In this video, we're going to take a look at simple examples in Verilog and ModelSim of the three principal ways how we can use Verilog. And that would be for structural description of circuits and behavioral description. And behavioral description splits up again into continuous assignments and into procedural assignments. There are two big hardware description languages, so that would be HDL, and that stands for Hardware Description Languages. And the two are Verilog and VHDL. What we're going to use here is Verilog, and we're going to look at the basic methods that we can use in Verilog for describing hardware. And the simplest of those and the closest to drawing schematics is a structural specification, where we actually specify in terms of AND or NOT gates and so forth what our logic circuit is supposed to look like. And those circuits are going to be interconnected using nets or wires. So there are going to be continuous connections between the individual components in that specification. And then there is the behavioral specification, where we do not tell Verilog what we think the circuit should look like. We just tell Verilog what we think the circuit should be doing. And there are two distinct versions here of doing a behavioral specification. One is a continuous assignment, which again uses nets and wires for the connection between components. In this case, just components that are specified on a behavioral level, like, for example, a multiplexer. And then we have procedural assignments, where we can use such things like if-else, or we can use a while command, or we can use for and then do something, or the case statement would go in here. And those are assignments where we again just specify what we want the logic to do, but we specify it not on a continuous basis. We specify it on the basis of if a particular input is changing, then go and look through this procedural assignment and check if the if-else, for example, needs to be evaluated in a particular way. So this only gets evaluated when something changes, and the output then needs to be stored somewhere. And so this doesn't go to wires or nets, this goes to registers. To see those different specifications in action, we are going to use look at the very simple example. We're going to take the function f is equal to x not ANDed with y. So this is the structural specification, of course, of that, and or the schematic of that. And when we do the structural specification, we just simply tell Verilog that we want to have a NOT gate with an input of x and an output of a. So when we specify this here, the first element in those gate specifications is the output of the gate, and then the rest of it are the inputs. So here are two inputs for the AND gate, one input for the NOT gate, and we could make an AND gate with 3, 4, 5, however many inputs that we want by just adding more in the description here. So we basically tell Verilog to use an inverter, produce the output A from the input X, and then to use an AND gate and produce the output f by ANDing a and y together. Then the continuous assignment. Here we are not giving the structure, we're just telling what we want, and we use the assign statement here. So we assign f equal to, the tilde here means not, x, and then the ampersand, that means and. So we do not x ANDed with y, and we assign that to f. And how Verilog is going to implement that is going to be the problem of the compiler that is looking at those commands. And then finally, the procedural assignment. That has to go into what is known as an always block, or in general into a procedural block. So this is called an always block. And that always block has a sensitivity list. In this particular case, the sensitivity list just contains the two inputs x and y, and it is actually going to look at the levels of x and y. It's also possible to specify either the positive edge or the negative edge of an input that it should react on that. But for now, we just stick with the levels here. And then we use an if-else statement here. So if x is equal to 0, so double equal sign means equal to, and y is equal to 1, then we make our output 1. So the f1, and then the apostrophe b1. So 1 apostrophe b means that we use 1 position, and we're going to specify this in binary. So 1 position means 1 bit. We specify this in binary, and then we give it an output of 1. Okay, so this is the value 1. And then if that is not true, then comes the else clause, and f is going to be 1 apostrophe b0. And the 0 here, that stands for the value 0. The 1 apostrophe b again stands for the fact that we just use 1 bit for that, and that we specify this bit in binary. The key thing to remember here when there's a procedural assignment is that the output f in this particular case, or outputs in general, must be registers, because we have to store the result of going through that procedure. We do not have a wired connection in this case between the input and the output. We just have this looking at what x and y is at some point in time, namely when x or y changes, and then producing an output, and then that output needs to be stored until the next change in x and y occurs and a new computation is made, which is then stored again in the register. So now let's start ModelSim so that we can actually try to input those things into ModelSim. I'll try to move this over so that it shows up in here. So we have the jump start here where we can set up a new project. So if we click on that, then we will see the welcome screen. We can either create a project or open a project. So we're going to create a new project now. We're going to give it a name. So it's going to be simple example. And we choose a location for storing that. I'm going to choose a location different than the default so that I do not get any conflicting files set up and so forth, and I can reuse that later. So I go to ECN 2350, and then in here, and here I have my ModelSim directory, which I have set up for that purpose. And I'm going to choose simple example as my directory. And then I can click on OK, and now I can add or create new files. So the first thing that we want to do is we want to make the AND gate with a structural description. And we have to add the file as a particular type. You can see that it says VHDL here. We do want to have Verilog, so we choose Verilog, and then we click OK. And we close that for now. And then we can look at what ModelSim has created so far. So if I shift this down a little bit, we can see that we are actually in ModelSim. And now I'm going to double-click on that, or use any kind of editor in order to edit that file. So we have now this pane over here. And a Verilog module starts out actually with the keyword module. So we're going to put that in. We're going to call this AND and then struct, because we are looking at the structural description. And then we have to tell Verilog what the signals are that go in and out of this module. So we have inputs X and Y, and we have an output F. And then the semicolon. So in general, lines have to be terminated by semicolon. Otherwise, the compiler will complain later on. So we don't know at this point which of those things are inputs and outputs, or at least Verilog doesn't know. So we have to tell it that we have input X, comma Y. So those are our two inputs. And then we have an output, which is F. Again, the semicolons here are important. And then we make our structural description. So we have a NOT gate with an output A and an input X. And we have an AND gate that takes A and Y and makes an output F. So A, Y, semicolon. And you can see now that we have actually declared what X, Y, and F are, but we have not told Verilog what A is. If we do not declare anything further, it will assume that it's a wire. But in general, it is better to actually explicitly tell it that we want to have a wire. And this is called A. And then we're actually done with the description of that simple circuit. And we can now tell AND module. And I usually put in here what the module was. So that is the AND struct. You also get to see what the comment looks like. So this is a two forward slashes. That's a comment for one line. If you want to make a comment that goes over several lines, for example, I could do this at the beginning to describe this module. Then you do slash and the star. And then you can, for example, put a whole bunch of stars here and then write that this is structural description. And then finish that off here with another slash, and that is the end of the comment. You can see how the color changed. Everything was green. If I go back here, everything is green, so it thinks everything is a comment. And then once I put the star slash, that means that it's the end of a comment. Okay, so we can put that like this and save it. And then we can check whether Verilog is actually going to compile it. So we right-click on the file name here and choose Compile, Compile selected, and see what's going to happen. So we did the right thing here. It says compile of AND struct was successful. If for some reason we are making a mistake somewhere, then let's actually try that. Let's leave out one of the semicolons here. Save it again, and then compile it again. Then you can see that the compile now struct of AND struct failed with one error. And we can go here under the Compile tab and check what the compile report is. And it will tell us here that it's an unexpected output expecting a semicolon. So that was line 7. and line 5, so we can go back and take a look at what's happening at line 7. So line 7 is the one after the error has occurred, and line 5 it complained because f is now not defined because we were missing the semicolon here. Usually the errors are happening on the lines just before the lines that it flags as being in error. Okay, so we put that semicolon back in, and now we save it again, and we can compile it again, and that will work. Now if we want to test that this is really working right, we have to actually build another module that gives the necessary input, or creates the necessary inputs for x and y, and then displays what comes out in the form of f. So what we're going to do is we're going to add another file to the project. We're going to call that and struct and then underbar tb. Okay, tb stands for test bench, and that's going to be a Verilog file again. And we're going to edit now this test bench. So this is going to be a test bench for and struct. Okay, there's nothing particularly magic about test benches. They just have to create signals that can be fed into what we want to test, and then they have to have the capability of displaying what comes out of that. So this is going to be a regular module. So I'm going to write here module and then and struct tb. And there are no inputs to that. It's actually a generator. So we leave that those two parentheses empty. Then there will be some timing involved. And so what I like to do is to actually specify a time scale. That's not strictly necessary, but it's kind of useful. Time scale of 1 nanosecond / 1 nanosecond. So what that means is that the time scale at which things are happening is going to be 1 nanosecond, and internally it's also using 1 nanosecond. You can internally use smaller increments of, for example, 0.1 nanosecond if for some reason you need a finer resolution for some internal computations. Okay, if you don't put this in, then it will assume, if I remember it right, a default of 1 picosecond. Okay, now we are going to generate a clock. Okay, so let's actually see how we do that. It's something that will have to have memory, and so we have to make it a register. And then we are going to make another one of the procedural blocks. This is called an initial block, which means that it's run at the beginning when this simulation starts. And I'm going to put a begin here because I will put more statements in here. So clock needs to be somehow set to something in the beginning. If we have a register, that register is considered to be undefined at the beginning unless we specify what goes in there. And because we use the begin, we also have to use an end. Any procedural statement that has more than one statement in it needs to be enclosed in the begin-end sequence. And then we're going to make another procedural assignment. That's an always block. And we are going to do that regardless of what else is happening. We're going to do it with a #5. That means every 5 time units, we're going to do what we specify now. We're going to make the clock equal to tilde clock. And that means we're going to invert what the value of the clock is. So if it was 1 initially, then after 5 time units it will go to 0. And after yet another 5 time units it will go to 1, and then back to 0 again, etc. And in this way we're producing a clock that can be used as an input into our system that we want to test. Okay, so now we have a clock, but we need two inputs, so we cannot use just a single input for x and y. We have to use something different for x and for y. And we want to test all possibilities, so we want to test 0, 0, 0, 1, 1, 0, and 1, 1. So what that means is that we have to go back and make another register here, and this register is going to be a counter. And we need 2 bits in that counter, so we specify this by this the rectangular brackets there, and then going from 1, 0. So that means that we have a position labeled with index 1 and a position labeled with index 0. And we're going to call this count. So that basically sets up 2 bits in a 2-bit register that we can use for counting. And so now we have to initialize that count as well, because it's a register. It turns out that it's useful to initialize that to -1. And what's going to happen is that once the simulator starts, it will apply a clock to that, because we're setting the clock equal to 1. And so then it will actually go to 0. So the count will start at 0 if we preset it to -1 before the simulation starts. And then we use another always block. So that's another one of those procedural blocks. And that is going to be sensitized to the clock, and in particular to the positive edge of the clock. Okay, so we indicate that by saying pos edge clock. It's also possible to do neg edge clock, but we basically want the counter to react not on the level of the clock signal, but on the transition of the clock signal. And then when that condition is met of that positive edge of the clock, then we make the count equal to count plus 1. Okay, so in this way we're counting from -1 to 0, then from 0 to 1, from 1 to 2, from 2 to 3, from 3 to 4, etc. But because we have only 2 bits, it will actually wrap around. Once it has reached 3, it will go back to 0, and then 1, 2, 3, 0, 1, 2, 3, etc. And now comes the point where we are actually looking at the module that we want to test. So the module that we want to test is the end struct module. Okay, so we tell that to Verilog by putting that in. And then we have to have a specific instantiation of that module. And we're going to call that MUT. That needs to have a name. MUT stands for module under test. But you can use any name that you would like to. The MUT is just kind of a convenient one. And then we have to have an input x into that module. So we're going to put count 1, bit 1 of the count, into that part. And then there is a count 0 that we're going to put into the y input. And then we're going to have an output f. Okay, now the output f is something that we have not declared yet. So by default, it becomes a wire. But again, it is better to specify that we have such a wire. So we're going to put that in here, wire f. Okay, and then we are essentially done with our description here. All we need to do is finish the module by putting end module. And that module was called end struct TB. So the test bench for that end struct. So now we save that. We compile it. And the compile was successful, so it didn't make any mistake. And now we can simulate the whole thing. So now we can go and click on the Simulate tab. And we click on Start Simulation. And then we have to go here under Work and find the the test bench that we want. So it's the test bench that we are executing, and the test bench is going to make an instantiation of that module that we actually want to test. So we click on that, and then OK. And so it will take a while, and then some panel comes up which has a whole bunch of things in it. It has over here on the left the struct TB, so that's our top-level module, and then it has the MUT, that's the module under test. If we click on this, we can see that it has a NOT gate in here, it has an AND gate in here, so that is hierarchically at the lower level than the test bench. And then we want to see now, we want to run that simulation and see what the output does. So we right-click on the module of which we want to see the output, and we click on Add Wave, and that will bring up a wave display that will then get populated once we run the simulation. So we can see here that there are 3 signals from the struct TB module from our test bench. One is the clock signal that we produce, one is the count that we produce that has 2 bits, and then one is the F. This is the output that comes back from the module under test. That's where we are going to see whether it's doing the right thing. We can also add the module under test itself. So if you right-click on the MUT and we add the wave, then that gets added here so that we can see, for example, the internal signal A inside that module under test. And then we're going to run it. We use the clock cycle of 2 × 5 of 10 nanoseconds. And so we, for simulating all of it, we will need at least 40 nanoseconds. The default here happens to be 100 nanoseconds, so we can just leave that and run it at the default of 100 nanoseconds. So if I click on this, actually that was the restart, so we cancel that. I have to click here to the right to run it. So I could also click on the run symbol, or I could do F9, and that will produce my output. Now, in order to see that better, I do a right-click on it, and then I do a zoom full. And now it gets zoomed over the full width of the window. And I can see here is my count. Count 00, 01, 10, 11, 00, 01, 10, 11. So it repeats here. Up here at the top, we have the clock. Every 5 nanoseconds, down here is the scale of the nanoseconds. Every 5 nanoseconds, it changes the value from 1 to 0, from 0 to 1, from 1 to 0. So it makes a total period of 10 nanoseconds for each clock cycle. And my outputs now are going to be changed in that rhythm of the 10 nanosecond periods. So we can see that F is going to be 0 when the input is 0, 0. It's going to be equal to 1 when the input is 0, 1. So 0, 1 means x is 0, y is 1. And because x gets inverted, that is the correct result. Then when we have 1, 0, so x now is 1, so that will, and y is 0 actually, so that will produce an output of 0. If we have 1, 1, the x is 1, and so the x naught is 0, 0, and that will produce an output of 0. So we can actually verify that this is correct. And down here we have the same f, but from the actual module under test, whereas the upper one here came from the test bench, where we were actually getting that result back from the module under test. And we can also check that the A here, the output of the inverter, is correct. So that is the output of x. Here, the first 2 periods of the clock, x is 0, so the output has to be 1. For the next 2 periods of the clock, x is 1, so the output has to be 0, and so forth. So this is quite handy to actually see whether things were happening the right way. To get out of the simulation, we can click on Simulate again and end the simulation. It's asking us whether we really want to quit. And we do want to quit at this point in time. And then we get back to the editor here. And if we click on Project, we also get back to the project symbols here got a little bit moved around, and we have a little bit less space now, so we can correct that by moving this up and bring this down. And so now we can go and do our other two implementations of Verilog of this simple circuit.